Good morning, good morning, good morning, good morning. There he is. There's the Colin. There's
Morning.
good morning, good
Good
morning.
morning.
And there's the Brandon. Good morning, good morning. And there's the Xavier. And when I say thee, I mean thee. All of thou. So good morning, Colin, Brandon, Xavier. Good morning, Charlene, Alexis, Anissa, Brittany. Good morning, good morning. Good morning. Sorry, and now I could have sworn I saw. Who did I just miss? Okay, okay. And the chat will get rolling, I promise. I know. By second semester, the good mornings take less time. That's not even true. Good morning, Gaia. Good morning, Ryan. Good morning, Alexis. Good morning, Adenelsi. Good morning. Oh, okay, morning, Charlene. And good morning, direct chat person. Okay, we'll just get started. Again, I'm just going to say what the exams are coming. Some of you have noticed you've gotten an exam back. Some of you have noticed you have not yet. They're just coming. They're just coming. And I'm just they're still just coming. Okay. Um and by the way, so far I think they're good. I mean, but I don't want to get that's like a anyway. Uh but again, no matter what, whether you got an exam and you have questions about it, or you didn't get an exam and it's getting you edgy, just reach out. Just text me. I mean, text, I mean you can email too, but either way, whatever. Just reach out and at worst we'll have a phone call and we'll just address things. Okay, so I want to get back to physics. Hold on, what's happening here? Um, and I also know that last class I made a mess of the computations. I'm sort of an unusual mess. I mean, hopefully, so you should also reach out to me about that or ask now if there. Oh, I guess I have to finish. Okay, I guess I should. I was about to do something. Let me just think for a second because I know I didn't actually finish going over that. Yeah, all right, all right. So let me back up for a second because I know last class was a mess. I mean, it's always kind of a mess, but I mean, I think it was sort of an unusual level of mess. So let me at um first of all, definitely, if I left you with any questions or confusions about that sheet, work by constant forces, feel free to ask them now. I was about to move on, frankly, to the next one, but I just remembered, that you may be left a little bit unresolved. So I'm going to quickly, so I'm pulling it up, the last sheet. I'm pulling it up right now. So feel free to ask any question about anything that I said two different ways or anything like that. And I'm just looking at it. Hold on. And if you're in the chat right now, I'll see it in 1 second. And someone's here. Hold on. Or did it already give the Well, yeah, actually, all right, someone's here. I know. Two people in the waiting room. Is there anything in the chat? I mean, well, okay, I'm looking in the chat. Let me just say again. Wait, yeah, actually, I'm going to leave it like that. I'm going to say this. I'm going to pause for a second. If there's anything anybody wants to see from the last sheet, either anything I just didn't address at all, or something that I addressed in a confusing way and you want clarification, I'm going to put it on you slightly. I'm going to ask you, I'm going to pause right now if you have any questions about the last sheet, about work. I know I didn't go over the whole thing, but about therefore. Anything you want to ask about work done by constant forces, I'm going to ask you to ask it right now. I'll pause, I'll give you a moment. But if not, but if not, then I'm going to move on to the next subtopic. Partly because if it was already a little bit confusing and you've had enough of it, I don't need to make it more confusing. So, like of my own initiative. So, and to be totally frank, also, I think this next subtopic like makes that last topic sort of easier in retrospect, easier to understand in retrospect. The next sheet makes the last sheet easier to understand in retrospect. So I'm going to pause for a second. If there's anything anybody wants to see at all from the last sheet, from work done by constant forces, this would be the time to say it. I will pause, but if you don't say it now, then I'm going to move on. Then I'm going to move on. So I'm going to pause for a second. I'm also going to look at something while I pause. Okay. I'm letting someone in. All right. So, so I'm going to take that I should or can move on a little bit. When I say move on, what I mean is I'm moving, well, I'm moving to the subtopic of work done by changing forces, which would be the next sheet, the sheet, I think it's homework number 9, um, which many of you have turned in. Thank you. Many of you have not. I understand we're all a little bit behind, but many of you, I see that 10 of you turned it in. Thank you very much. Um, Also on that note, there's one more homework done. Sorry. No, I'm looking at the wrong. Well, 6 of you have turned it. Okay. Um, there's one more homework for the whole semester. It was due this Wednesday. Somebody very kindly in an email sort of or very tactfully pointed out it was a little bit intense to try to do that right now because we haven't talked about it fair enough. They were very polite about it. So I've extended that, I've changed that to be due a week from today. And that's the last thing. And then your last class is Wednesday, I believe, right? Please. Yeah. And so by then you'll have everybody will have their exam bag and we'll talk about the final and all that stuff. I mean, by next week, and we'll talk about the final. But so anyway, so we're all just catching up. So what I'm talking about now is the topic of work done by non-constant forces. And in so I'm going to talk a little. I'm going to address the topics of this next sheet, specifically like it gets into springs. I'm going to address springs now. I'm not going to be directly saying things about the sheet, at least not at first. So this is like lecture, if that makes it. It's all with regard to homework 10. Um, okay. So what I want to remind you, work is by definition the path integral of force. That means work is the integral of the dot product of force with respect to displacement. That means if you are it that means if you are pushing or pulling an object through along some path, some one-dimensional region of space, some displacement, right? If you're pushing or when you're pushing or pulling an object through a one-dimensional region of space, then the concept is that every step you take, you ask, what is the component of force parallel to this step? Like, or every bit of displacement that the object undergoes, you ask, how much of the force that I'm exerting is parallel to this displacement? You multiply those two things together. You take that product, that those newtons times those meters, i.e., those joules, you put them in your mental bag. You take the next step. You do that product again. You you take that value, put it in your bag, take the next step, and you step all the way in your mind, obviously, but you step all the way from the first location X1 to the final location X2. And so what you will have done by the end is you will have added up all of the dot products. You will have added up all of the matching force displacement products from the beginning of the path to the end of the path. And you will have done this in a situation where the assumption is that the force is a continuous function of position, right? The assumption is that if the force is changing at all, it's changing in a smooth, continuous way. It's not changing like meter by meter by meter. It's not even changing by half meter by half meter by half meter. It's changing, but or it's constant, but it's doing whatever it's doing over intervals that are so small that they're infinitely small. You see what okay. And again, stop me if you don't understand this. I'm literally trying to simultaneously explain I'm trying to do three things here, really. And by the way, also everything I'm saying right now, everything that I've been saying at the end of the semester about work and energy, and then the very last bit that I'll say about gravity, like which is the very last bit, everything I'm saying now is like really directly meant to make your life at the beginning of physics 204 a lot easier. I mean, just for whatever it's worth. If it sounds like if I'm getting very theoretical or abstract or something, or if it's getting very calculusy now, it's all because this is the stuff that we begin physics 204 with. Okay. And so the more we can sort of get it now, the more really you'll be much more comfortable at the beginning of 204 for what it's worth. Okay. Um, so I'm trying to do three things simultaneously, really. I'm trying to explain the concept of work. In so doing, I'm trying to get across this idea of a dot product, which is when you multiply the parallel components of two vectors together to get a non-vector. And I'm trying to really drill down on really what is meant by an integral, even though we all know you've seen them before. But I think we all also know that for many of us, just because we've seen them before, doesn't mean we were ever that comfortable with them. At least I wasn't when I was at this stage of physics. So I'm really trying to use work as a way of getting you to really understand what an integral is in the first place. So please tune in that. I know I've said that a million times, but this is in my attempt to reassure you that it's not that I'm not, every time I define work as an integral, it's not because I'm assuming that that makes it immediately clear to you. It's really because I'm sort of trying to get across both at the same time what work is. So if you kind of get what work is, then use that to picture what an integral is. If you kind of think you already knew what an integral is, use it to get, you see what I'm saying, right? Okay. So last, again, I'm saying what an integral always is a continuous sum of products. Like it's written that way because it's really a big S. And the products that you're always multiplying are, but it's like a smooth S, right? It's a continuous sum. That's where infinity or infinitely small comes into play, why calculus is coming into play. And what you're always, in any integral you ever do for the rest of your life, what you're always doing is continuously adding up a product, which always is the value of the dependent variable times a little interval of the independent variable. That's like always what it is. That is why we think of on graphs, why we think of the integral as the area under the curve. Like it sounds so out of nowhere and obscure. Like, why would you want the area under the curve? That's just a fancy way of saying, like, if you go some interval, if you consider some region of the independent variable, like how much happened with the dependent variable during that region. Those rectangles that you picture under the curve when you're first learning about integrals in calculus, like area, rectangle, 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 and you add up all the rectangles. If each one of those rectangles is what I'm trying to say, where you take a little step along the value of the independent variable, and then you look up and you ask yourself, what's the value of the dependent variable? And you multiply them together, right? So it's like a width times a height of a rectangle on a curve when the curve is the function dependent variable of independent variable. So in this case, in physics, the height of each rectangle is force. And the width of each rectangle is displacement, like literal um, step in literal geographical space. Okay, that's what the integral is. I'm just changing the view on the screen. That's just like a review or whatever. But now, why I'm yelling about it is because the whole purpose of the integral, what like why we can't just say work is force times displacement and be done with it, which in fact maybe you did say in high school or people say in like more what which you could get away with in the I mean to step back, what you might have noticed in the entire first sheet that you just did or that some of you were still going to hand in, no matter with all my complicated talk, every time in the end in sorry. Well, okay, I see the thing in the chat. Let me address that in a minute. Let me address that in a minute. Um, a very fair question. Let me just finish this thought and then I'll get that. But I'm glad people are. Um, um, what am I trying to say? Oh, so I'm just trying to say you might have noticed on the last homework that anywhere you calculated work, what ended up happening is you were just calculating force times displacement. Like you might have consciously or not, you might have even had a moment or two where you're like, all this talk about calculus and integrals and stuff, but like in the end, isn't it just like work is just like force times displacement? Like what is all of his nonsense? All Gabberbaum's like talking about this. Well, what was happening on the I'll write it down, and I'm not forgetting the chat. Just give me a second. Um, to be quick about what was happening is if the force is constant with respect to displacement, then it comes out of the integral, right? And if you think about it, that really, that whole rule that you learned in calculus, that when something is constant with respect to the integration variable, it comes out of the integral, that's not just like an arbitrary rule. If you really think of an integral as a sum, like what it really is like f1 times delta x1 plus f2 times delta x2 plus f3 times delta x3, etc. Like that's what the integral really means. Then if all the f's are the same, if all of them the same, then it's f times delta x1 plus f times delta x2 times f times delta x3, et cetera, et cetera, et cetera, right? So you can just factor out the f and you can just factor it out. And then it just distributes all over all the, right? Like there wouldn't be a need for the calculus or there, what we're saying about integrals is that they reduce to simple, they are the sums of lots of little products. But when all the products are the same, have the same dependent value, then it's one big product. That's all, right? So yes, the integral reduces to a simple multiplication in all the cases where the f didn't change. We didn't that we need the integral to cover the more general situation where the f changes as a continuous function of displacement. That's where the calculus really comes in, and that's what I want to develop, like talk more about now today. And yes, what the second to last homework is really more about, but I will distill it down to its essence, to the main point you have to take away, especially for Physics 204, and therefore I can now answer the question that's in the chat. But let me think about the answer for a second. So the question in the chat is, are we going to have the last two homeworks on the final? They're both due this week, but I don't know. I mean, fair, I see what the person's saying. Like you might feel like we're really, I mean, you correctly feel that we're like a little bit rushed now and a little bit behind and stuff like that, which always happens. Um, um, so I mean, the simplest answer I can give is the thing, put it this way, anything that I cover in lecture for the next couple of lectures will be on the final to the extent that I covered in lecture. Like what? So, like, for example, I'm about to talk about springs right now. And I'm about to talk about potential energy, which is really what the last homework is about. That will be on the final. I will be more clear. I will, but it won't be in as detail as the Newton's law stuff. You will, I will adjust the sample exam so you'll be totally clear on exactly what's the final. Like you'll have a sample exam to look at beforehand, just like before. And those won't be, it won't be as to the level of detail as Newton's laws. But the rule of thumb to answer that question is whatever I cover in lecture over the next few days, yes, is on the final. But if I don't cover it in lecture, if there's details of those two homework sheets that I just never address in lecture, then right, then you're just doing those homeworks for points or for practice or to get you ramped up for next semester. But if it's on the sheets and I didn't talk about it, then you don't have to worry about it for the final. I mean, I think that's the most honest and best answer I can give. Um, okay, all right. Well, tell me if that and I'll repeat that as we get closer to the final. But um okay. Okay. So this what I'm about to tell you again, this is like just to be totally clear, what we begin physics 204 with is springs, and then it goes off in like a deep kind of abstract direction. And physics 204 is more abstract than 203, for good or for bad. But it begins with springs. And you see springs are all over that 11th homework or 10th homework. So let me address springs directly to you. And specifically, okay. Oh, so wait. Oh my God. All right. I won't get, there's something else in the chat. There's only one thing in the chat, and it said I shouldn't get sidetracked by it. So I won't, that, but I am emotionally inside. That's very kind of you. I totally appreciate it. Especially since, anyway, okay. Coming from you in particular, person that's in the direct chat, it means a lot. Okay. So here's the deal with springs. Or what you might call the like okay, first of all, anything springy, anything that's elastic in the world is a material that we can treat as though it was made of lots and lots of springs. Whether it, like a mattress is made of lots and lots of actual mechanical coils of metal that are sticking there. But something like what did I just say? A mattress, right? Some things you can't literally see the coil of metal, but some things are very elastic and they're very springy, even if you can't literally see a coil of metal. And if they're springy, it means that physics wise, they are made of individual springs that exert what is ultimately known as an elastic force. And an elastic force works in a very particular way. Like I'm going to explain the math right now, and hopefully you'll see that the math captures what you sort of always intuitively knew to be what springiness is. The ultimate point of, of a spring is that, first of all, every spring has some position known as the equilibrium position, or what mathematically we would designate as x equals 0. Meaning, if you imagine like one end of the spring, and I'm talking about a good spring, a well-behaved spring, like a spring that's very long, a spring that's uniformly tight, a spring that's well designed. If which really, okay, honestly, again, it means it's longer than any length that you ever subject it to, like substantially longer than any stretchiness that you ever subject it to. That it's tight, and not only tight, but uniformly tight. Like it's not more tight over here than it is over there. Okay. And that it's very light compared to anything that you're going to place on it. That's what makes a good spring, those three things that I just said. So imagine now you have a good spring where one end is fixed to like a wall and the other end is free to move back and forth. And we place some kind of some mass on the other end, some mass of m. And again, the assumption is that the mass of m is so much bigger than the mass of the spring itself that on any scale that would measure the mass of the mass, like the spring mass would come up as zero. Okay, like that's totally realistic. That's just a matter of comparative measurements. Wait, so Ooh, great question. Also from the direct chat person who does this apply, he or she asks, to rubber bands? Yes, everything I'm about to say. I mean, a rubber band, a good rubber band, as long as it follows, the simple answer is yes. Something doesn't literally have to be coiled up to perform the function that I'm like about to describe. As long as the thing is I mean, rubber bands are harder to make really good because one of the requirements here is that whatever tightness there is over here has to be the same tightness as over there. But if you fix a rubber band properly, like whether it's to one wall or you put it around a pulley or something like that, if you fix a good rubber band properly, yes, it is the essence of elasticity. Yeah, good question. Which is this. If I put, once I set up one end of this elastic material, the other end has an equilibrium position. Like there's a position where the other end would automatically sort of find. And if you know it's an equilibrium position because if you place, and again, I love the rubber band question, but everything I'm about to say is like easier to picture with an actual metal coil, which you'll play with in the first lab of next semester. Um, so it's just easier to picture. The other end of the spring, if you place the mass on this spot called equilibrium, you'll know it's equilibrium because you place the mass there and nothing will happen. The mass will just stay there. Whereas if you place the mass anywhere else, if you hold the spring out to the right of equilibrium, or, well, if you hold it out to the right and you let the mass go, as of course you know, like the mass will start zooming in toward the equilibrium. Or if it's a really good, well-designed spring, if it's really actually properly designed, like super long and uniformly tight and all this kind of stuff, then even if you set the mass to the left of the equilibrium, like if you compress the spring, right? And you let the mass go, then it'll start moving out once you let it go toward the equilibrium, right? So equilibrium is the one and only one spot where if you place the mass there, it would stay there. And we call that place x equals 0. Again, we're measuring x. We're measuring the end of the spring that is not fixed. And when we talk about x, excuse me, when we talk about x, we're talking about the position of some mass that we're like some particle that we're focusing on at the end of this spring. Okay, and I think everything I'm saying is like already, or you can picture, I hope, or tell me if you can't. But now here's the thing that makes springs springy. I mean, okay, so on the one hand, there's this equilibrium position that the mass is sort of always seeming trying to get to. Just like with gravity, there's a ground level that objects are always seemingly trying to get to. Like if you hold something above the floor, it falls to the floor, right? So in a way, there's a similarity between springs and gravity in that they each have an equilibrium position associated with them. But Whoop. Okay. The first thing I want to say, and I'm going to give you more pictures, I'm going to give you graphs. The law that really ends up defining elasticity, defining the action of a spring is this law, Hooke's law. And the law is F equals negative kx. Like F and X are vectors. They have direction associated with them. Like, okay, and as this diagram is trying to show, like if generally speaking, if X is positive, what we're picturing is extension, and if X is negative, we're picturing compression. I mean, you can set it up any way you want as long as you're consistent, but that's like the tradition. So the first thing we're saying, the first, well, okay, hold on. Hold on. Well, I was explaining. Okay. First of all, in terms of so what is this F equals negative kx? What does it mean? Okay, the negative sign is an indication of direction. It's literally saying that the force is always in the opposite direction from the displacement. Displacement what? Displacement from equilibrium. Like if equilibrium is x equals 0, any value of x means we're measuring from the equilibrium spot. We're measuring where the mass at the end of the spring is. So if the mass is like way out here on the right of the equilibrium, if the spring is extended, the spring force tries to pull the mass back to equilibrium and vice versa. Again, you already knew this, right? I mean, this is a big part of what it just means to be elastic. You push it down, it tries to come back up, or if it's a mattress, for example, right? So we call that a restoring force. If the force is in the opposite direction always from our displacement from some equilibrium position, the force is trying to restore us. I mean, it's not trying to do anything, but it's directed so as to restore us to equilibrium. That's the direction. That's the negative sign in the law. But now what's a little bit more interesting maybe is the magnitudes. We say F equals negative kx. Now, if k is a constant, I'm going to talk about this constant more in a second, but if k is some constant for a given spring, one spring might have a k of 100, a different spring might have a 200. I mean, I'll get into what that means in a minute, but if it's a constant, then this equation is like y equals mx plus b, but except b is 0. Right? Like well, with this equation, in other words, this equation is not saying f equals negative kx squared or something like that. Or right, it's just saying f equals negative constant times x. So it's saying that f is directly proportional to x. This is actually where things get interesting. This math is not crazy hard in and of itself, right? I mean, comparatively, like I'm not saying this is involving calculus in and of itself, but although I am saying it's going to prompt some calculus, I'm saying that for the first time now, we have a force that varies with respect to position. That's like the interesting news. That's the advancement. Like, notice this is unlike gravity, or at least it's unlike mg. The force of mg is mg whether an object is at 3 meters above the ground or 7 meters above the ground or what, like the force that tries to pull it back to the ground is its mass times 9.8 meters per second squared, right? So it doesn't matter how high it is above the ground, it's going to be pulled back to the ground by its own weight, which is a constant. So with gravity, whenever you're calculating the work, as you did in the last sheet, you set it up as an integral. But and then this is again where I sort of got like all in my head last week. But when you're calculating the work done by gravity, you set up the integral of mg dx, but mg doesn't have any x's in it. It doesn't depend on x. So it comes out of the integral, and you end up just having like the work done by gravity is always the force of gravity, mg, times the height that something either went up or went down, h. And that's it. Like, okay, that's a reminder or a review or whatever. The big takeaway, and that is on the final, I mean, for what it's worth, like the big takeaway from the last sheet is that the work done by gravity is always just m over some height h is always just mgh. Because even though in principle work is defined to be an integral, the integral becomes trivial in the case of a force that is constant, such as gravity. So with gravity, the work is always mgh. However, in contrast, here, for the first time in physics, we have a force that actually cares where you are. What this law is saying is that if you pull the mass out twice as far, the spring is going to exert twice as much of a force to get the mass back to equilibrium. And this is what it really means to be elastic. This is why gym equipment is made of spring. I mean, not that I know about it, but I've heard of movies about gyms. But right, like if you're like gym equipment or mattresses, whatever it is that or bumpers on cars, whatever you think of as springy, what you're really thinking is that a spring is harder to hold stretched out here than it is to hold it here. It's like literally harder to hold it here, right? And it's hard. And like the more you're trying to pull, again, I don't know, I've never tried, but like the harder you're pulling it, I mean, the farther apart you try to pull a spring, you actually have to exert a harder and harder force. That's why it like challenges your strength in an appropriate way. Hopefully you see. So this is a new mathematical idea in our physics study, a force that is not constant with respect to position. That's like the bad news or the interesting news, the challenging news. The good news is it's changing in as simple a way as possible. It's a straight line function. It's direct proportionality. If there was going to be a change at all, this is the simplest possible change we can imagine. That's why we love springs so much. I mean, we love them for their physical effects, but mathematically, they're very worth studying because they represent this like next step in force and work examination. So now I want to talk about the K. Okay, so I'm going to bring. I'm just looking at the chat. Okay, so what I'm saying is this. So again, whatever I'm talking about right now is like the elastic force in general. Any material that is elastic can be thought of as being made of many, many individual simple springs, like the one I just drew. So this is the force exerted by any one of those individual springs. You can think of it this way. Okay, I'm saying if you would imagine a graph of like how hard the spring, like how strong a force is the spring exerting as you pull the mass out from equilibrium to various positions. Well, right at zero, right at equilibrium, the force is zero. The mass won't accelerate, it'll stay there. If if you pull the mass out to like 1 meter, the spring will exert a force on it and try to pull it back to equilibrium. So it's in the negative direction compared to the displacement. So that's why like my entire graph is in the fourth quadrant, right? It's going down because as the displacement gets increasingly positive, the force gets increasingly negative. And also we continue up into the second, I guess, yeah, I guess I should say that. Um, And notice the force gets stronger and stronger as a straight line function of the displacement, like F equals negative kx, as opposed to F equals negative kx squared or cubed or something like that. It's linear. It's y equals mx plus b, right? But now let's talk about the m, so to speak. Like the slope, like straight line means constant slope, right? What is the slope in this case? Well, it's rise over run, of course, but the rise here that we're talking about is force units, newtons, and the run is delta x, right? So I'm just looking at the absolute value of this right now. So the run, the rise over the run, the amount of force per meter is that constant that we call K. K is some number whose units are newtons per meters, right? That's what K, like in other words, I'm saying mathematically, K is just the absolute value of the slope of this graph. K is how much rise you get per run. In physics terms, that means how intensely is the spring pulling for every meter of displacement that you ask it to stretch or compress. So K is measured, for any given spring, K is a constant number measured in newtons per meter. It's how strongly the spring pulls for every meter of displacement. In other words, K is the spring stiffness. If a spring has so every individual spring, like a good spring that you might buy in a box for a lab or whatever, it'll have a label on it. It'll be like K equals 300 newtons per meter versus another spring might have K equals 50 newtons per meter. The one with 300 newtons per meter is a stronger spring. For every given meter of displacement, it's pulling 300 newtons. Now again, and I'm going to move on in a second, but that's so K is a characteristic property, a material property, technically what we call a parameter to describe a spring. If the spring is 300 newtons per meter, that's very strong. But that's what it means, newtons per meter. It doesn't mean that the spring is always pulling 300 newtons, right? It means for every additional meter that you pull the spring out, it'll work with an additional 300 newtons of force, right? It's a ratio. It's the slope of the force displacement graph. So, okay, so I'm just looking at the chat. Okay, so that's how springs work. I'm going to just pause for a sec. Like now I'm going to try to like do math on this or apply this to physics or, but from now on, I want you to know this. I mean, this is a big takeaway. Like, and again, you can do the homeworks at any time for the points if you want to do the homework, or if you're so behind that you can't handle the homeworks at this point, I can relate. Like, no one's being punished for not doing homework, but you get more points for doing them, obviously. And even if you do it imperfectly or only some of it, you'll get some points, whatever. Like at this point in the semester, if you want to just consider it all extra credit, that's fine. But if you want to know what you need to know for the final or for next semester, the big takeaway is this: what I'm describing right here. All springs from now on obey F equals negative kx, and that means that the restoring force exerted by a spring is directly proportional to the displacement undergone by the spring. That's what I'm saying. So I'm going to start like applying this now or doing examples or whatever, or I'm going to start applying it, but I'm going to pause for a second. Any questions on that, or does that make sense? Okay. Can I just get like some electronic hands if I'm good to go on? I mean, should I go on? Have I lost everybody? Yeah, thank you. Whew. Okay. Thank you, Nes. Thank you, Vicky. Thank you, Nesreen. Thank you, Ada Elsie. Thank you, Charlene. And okay, great. Awesome. Good enough for me. Thank you. Okay. I need that. Okay. Okay. So why this is coming up? Oh, all right. Fair enough, direct chat person. Oh my God. This direct chat person. Yes. One day you're visiting me in my office and you're making this up, but okay. Anyway, yes. Fair enough, direct chat person. Okay. And there's only one, so you know who you at the moment, so you know who you are. I'll bear this in mind. No, I'm not distractible at all. Okay, so the question is, what is the work done? So why we're worrying about springs? Well, first, they're very useful. They're like super. I mean, and like all of physics 204 is like based on them for good or for bad in a weird way. But also we're caring about them because they're the first example where when we calculate the work done by something, we like actually have to think through the force. And this is the first example where where it starts to make it clear why we care about work in the first place. Like, because honestly, if forces were always constant, we wouldn't really need to get that involved in the whole idea of work. But it's when work forces are changing that F net equals ma starts to become very inconvenient to use. So, and springs are the first. So, so what is the work done by a spring to restore a mass? Like, in other words, you put a mass, you hold a mass at x equals x naught, some initial position, right? You hold it there, but then you let it go. So now the spring will literally pull on the mass toward the equilibrium position, and it'll start moving toward the equilibrium position because the spring is exerting a force on it, so it'll displace. Now, when it gets to the equilibrium position, I haven't said yet. I mean, I'm not saying it's going to stop. In fact, honestly, I'm saying it's not going to stop because it's going to build up speed and build up speed. When it gets to the equilibrium position, it's going to keep moving for a while, and we have to analyze that. But right now, what I just want to know is for that period of space and time where it's being displaced from the endpoint to the equilibrium, like what, how many joules of work are being done on it by the spring? That's what I want to know right now. So I'll use the definition of work. Work equals the force exerted dot work equals the integral of the dot product of force with respect to displacement. And we, yes, we do work to get, well, yes, that's a good point too. Why are we worrying about all this work? To get money. Absolutely. Um, Oh my God, you guys. Well, you're definitely paying attention. Thank you. And I was a different direct chat person. So all of you need to visit me in my office at some point. Maybe I need to actually be in my office at some point. Um, uh, so work by definition is this. Here we want to know, well, from any one position to any other position. Here we want from some arbitrary position x naught to zero to the equilibrium. We want to integrate the path. So I'm just rewriting it again. Okay, so I'm applying the definition. Okay, well, first of all, by definition, what it means to do a dot product, right, is to do the magnitude of one force times the magnitude of the other force times the cosine of the angle between them. That's what it means to do the dot, to just multiply components that are parallel, right? Okay, now here I want you to just look at the situation. And this is again maybe what I didn't say very clearly on Wednesday. Cosine of theta means, like, okay, I'll try to, in general, when I say theta, what I mean is the angle between the force and the displacement. That's what I mean by theta. The angle between the force and the displacement, whatever that angle might be. Now, what I want you to see, and I want you to stop me if this does not, well, actually, you know what? We have a little time here. Tell me somebody in there. I'm going to wait for those three responses. I'm not trying to trick you. I'm just making sure we're all together here because again, I think this is the part that gets confusing to people or part of the part that get. So I'm just going to ask everybody. This is not a trick. If you think the answer is easy, you might be right. What is, in this case, what is the angle between the force? Oh, when you've let go, when you've let go of the mass. So now the spring is pulling it in toward the center. So the mass is going in like this, and because the force is pulling it in like that, what is the angle between the spring force and the displacement of the mass? What's the angle? In this case, not a trick question. I'm just going to wait till I get three things in the direct chat. Oh, that's very good. Okay, I see one thing in the direct chat. I'm going to respond. It totally shows it knows what the question is. I'm going to respond to it specifically after I get two more. I see one response in the chat. Thank you for that. I see why you wrote that. But I'll say this too. I'm saying this is while the thing is actually cut, like you've let go of the mass. So the spring is pulling it in, and in fact, it is going in. So the person that wrote the one thing in the chat, like, totally gets the question, is totally picturing everything right. But I might make a slight modification to what they said. But I want to get two other answers. What's the angle? I'm not trying to trick you. I'm just yelling because that's what I do. What is the angle between the force and the displacement as a horizontal spring pulls a mass horizontally, like along a tabletop or something? There's one answer in the chat. I would like two more before I go in the direct chat. What's the angle in this case between the force and the displacement? Awesome. Okay, I just got another thing in the chat. Now, granted, it was from the same person, but they just sort of modified what they were saying based on what I said. So they're totally paying attention. And yeah, I will explain this. There's a slight subtlety here. It's the second of your two choices, direct chat person, but I'm going to keep that to myself for a second. But can I get anybody else? I'm telling you, it's not meant to be a trick. There is a subtlety, so I could see one choice or another choice, but it's not going to be some obscure thing like 32 degrees. Like, how could it be? I didn't like tell you anything obscure like that. I'm going to wait for two other people in the direct chat just to say something, or to say, can you repeat the question or whatever? But the question is, what is the angle between the force and the displacement? I keep saying it's not a trick question. Maybe it is a trick question. Maybe it's so simple you don't even know why I'm asking. Like, maybe you're thinking that I wouldn't be asking it unless it was something complicated. I'm asking it because I'm trying to do the math here. I'm asking. There you go. That's that's a second answer in the direct chat. I'm going to say right now, I agree with that answer in the direct chat. So somebody's getting somewhere. I mean, people are getting somewhere. I'm only asking this because I've got to know in order to keep going with the math. I don't think it's the big issue of this problem. I think the big issue is the changing force. The angle is not the big issue of this problem, but I have to show you why it's not the big issue, if that's a hint at all. So I have two answers. I'm going to wait till there's one more. I don't know why but we have time. We're not behind. I'm behind on your work, but we're not behind on the curriculum. And you should know that, by the way. We're definitely not. Like you're definitely going to be set for 204 for what it's worth. But I'm waiting for one other person. Or I'll repeat, the question is what's the angle between the force and the displacement in this case of a spring? Or I'll even settle for just somebody putting in the chat anything like, just if you just show me you know what the question is and then say I don't know the answer, I'll accept that. Just someone the question is, what is the angle between the four? Well, that's interesting. Now that no, it wouldn't. Okay, same direct chat person. I'll address. You're definitely thinking about it. You might even be making it harder than it actually is. You're asking good questions, direct Petra. I'm going to say that to everybody in a minute, but I want to see if I can get one other person in the chat here. Um, Even the question is, what is the angle between the displacement and the force? If you even put that in the chat, I will move on. If one of you, somebody new, even puts that in the chat, even repeats the question, I'll move on. But can I get something here? Can I get it with? Okay, that's fair. I just got a third person who at least repeated the question but said they don't know. All right. The 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 mass is being pulled in like this, like the pull is toward equilibrium, and the mass is traveling toward equilibrium. The force is horizontal, and the displacement is horizontal. The angle between, yes, thank you. Yes, direct chat, new direct chat person. Yes, the angle is zero. I'm not trying to trick you guys. What I'm really trying to do is say, like, sometimes in these problems, the issue is the angle, like many of the problems on the last sheet, like when you're on an inclined plane or when we're dealing with gravity, or like sometimes the force and the displacement are not lined up. So you really have to take that dot product seriously sometimes. And even in some of those times, you don't have to take the integral that seriously. It, other times, like now, we really have to take the integral seriously. I'm not saying we don't take it seriously, but like we really have to worry about the details of the integral here. But the details of the angle are not the issue here. The angle in this case, and I'm going to address the angle in this case is zero. Now, let me say there were a couple of good questions. Is zero. So the cosine will be one. Okay. And I'm going to address the direct chat thing. So we're going to say here, like the vector aspect of this will go away. We're just literally going to have f times dx. Now, a couple of questions were in the chat. One person actually asked, wait, does that mean if this whole thing were vertical, would the angle then be 90 degrees? Okay, that's a great question. I mean, that's like obviously you're thinking to ask that. But the answer is no. If this whole thing were vertical, as will be the case at the beginning of 204, if the whole thing were vertical, then the whole thing would be vertical. The mat, like if you pull the mass, if here's equilibrium position, and you pull the mass down here and you let it go, the force would be pulling directly up, and the mass would displace directly up. What I'm trying to emphasize here, that I guess I want to practice a little bit, whenever we say angle in the context of the dot product, we mean between the two vectors, between, like not between one of the vectors and the ground or something, the angle between the force vector and the displacement vector. So a spring, no matter how you orient the spring, it causes an object to move in the direction that the spring pulls it, or at least along the axis that the spring pulls it. So with a spring force, the angle is zero. Okay, now one person who also asked the vertical question, which was a really good question, that person also initially was thinking about possibly the number 180 degrees, which really showed that they were really following, because I totally get why they said that. Because I am saying that f equals negative kx. Like this is a little subtle, a little confusing. I am saying that the force is in the opposite direction from the displacement. So for sure, while you're pulling the mass out to the right, the spring is fighting you and pulling to the left. So while you pull the mass out to the right, oh, the spring is doing negative work. Like then it's 180 degrees. Yes, the spring is fighting against what's going on. Once you let it go, F still equals negative kx. like the force is still in the opposite direction from the displacement from equilibrium, i.e., if the mass is at the positive 5 meter mark, the force will be pointing negatively. So they're still opposite to each other, right? It's still F equals negative kx. But if the spring is the only thing doing work, the mass is going to be cruising in negatively. Like it's going to be going from like +5 to +4 to +3 to +2 to 0, while the force pulls negatively. The work will be like, so they will be in agreement. If the spring, I know that's a little subtle and a little confusing. The spring will be acting opposite to the direction of the place that the mass is at any given spot. But the overall action, the force will be in agreement with, it will be successful. The spring will be pulling the mass successfully toward equilibrium. It will be giving it energy. It'll be speeding up the mass. It'll be positive work. So the angle is in fact 0, not 180, even though I totally understand. Anybody who thought it was 180 is paying attention for sure. But I think the answer is 0. Now I'm going to move. So in this case of from now on, with any springs, the cosine is not an issue. Cosine is an issue with other examples of work. It's not an issue with the spring. Can I get anybody to just give me an electronic hand to move on? Like, are we okay on the angle now? Can I get a witness? Okay, that was okay. Oh, great. And then some new people. Great. I'm not new, but new to the. All right. So now it's about doing the integral. It's not bad, but we got to do it. Like, so I'm saying work. The work that the spring does from x naught to 0 is the integral of f dx. Okay. Well, f is negative kx, right? So I'm plugging that into the integral. Now, one thing, now, again, maybe a Wednesday, if you ask questions, I'm going to say something now that I think is from your math class. I can explain it more on Wednesday if anybody wants. But I feel that from your math class, like, let's go this bit by bit. First of all, the negative sign, right? What can I do with a negative sign? Or if you want to write in the chat, I'd be really pumped. Oh, that's gym equipment. What can you do to get rid of a negative sign in an integral? What's one thing you can do to get rid of a negative sign in an integral? Like if you multiply the entire thing by -1, what happens to the integral? Well, I'll say, okay, I've been torturing you. One thing is, yes, you can certainly do that. That's very good. You can go like this. People really are with me. And then remember when at the end, when you evaluate integrals, you like subtract from one value to the other. Like we're going to do that in a minute. So you may remember that if you want to get rid of the negative sign, if you want to multiply the whole thing by -1, you can swap the limits of integration, right? Is that familiar? People know what I'm talking about? Well, I'm doing it. And I'm going to keep going. The reason you could take the negative out of the integrals because it's a constant. It doesn't change with respect to dx. Well, neither does k. So k also comes out, shifting it to the left like somebody said in the chat. So I'm going to say so far we have this. We have right? And what is the integral of x dx from a math class? This I probably should wait till I'm going to wait for one person. We're doing the integral of x dx, like mathematically. Close. That's the derivative. What someone just wrote, and that person is totally on fire today. It's totally noted that you're on fire in terms of participation and everything, and you should definitely submit for the points, which you will get, even though I'm totally behind with. But they are there. But yes, awesome. Right. If we're doing an integral, so I got like 3 people just went into the chat. Awesome. And all of you should submit for points because I know this is intimidating to some people. Awesome. Awesome. I see that. I'm not going to name names, obviously, but right, when you're doing an integral, you do an antiderivative, right? You do the derivative backwards. So you ask what function would, if I took its derivative, would get me x? And the answer is x squared over 2, right? Right? And then we're doing a definite integral. So we're evaluating it, right? So that means, um, one thing before I go to, I'm just going to check. Well, no, okay. So this is a takeaway here. I mean, you can memorize. I mean, this is always true what I just wrote, but oh. Oh, that's fair. Totally fair. No, yes, I appreciate that direct chat person. The takeaway, we've got like 8 minutes left. The takeaway here, we, the work done by gravity is always MGH. I mean, that was a takeaway from last time. Now I'm saying the work done by a spring is always the work done by a spring to get you from some spot x naught to 0 is always 1 FKX naught squared. And in any book or website or anything just calls that spot x, then it would be 1 FKX squared, right? I mean, you don't always have to call it x naught, but um, I mean, that will never fail you. That's always true. But the really important thing here is like, why is it true? How did we just get this? We got this from integrating. That's the work done by a spring. And yeah, and notice we had to integrate to get it. Like, I'm looking at the time. We have 7 minutes. Like, well, okay, quick. Quick example. If you had a mass on an end of a spring and the spring had a stiffness of 200 newtons per meter, so and you held the mass at 5 meters from equilibrium, the work that the spring would do to bring the mass in from to equilibrium would be 2,500 joules if you just plug into what we just decided. And notice that what we're really saying is the key that we're saying is like if you didn't know anything about calculus at all, but you did know that work was force times displacement, what you might think is, okay, the force is 200, like the thing is sitting there at 5 meters. You might think, okay, the force is like in magnitude kx, like 200 times 5, that's 1,000, right? And so the force is like 5,000 newtons right there at the edge, and that's true. And you think, okay, and then the thing has to move 5 meters, so I guess it's 1,000 newtons times 5 meters. Oh, 5,000 joules, you might think. If you literally just did like kx times x, in other words, if you did kx squared, which you might think if you knew that the force was kx in magnitude and the displacement was x, you would maybe think it would be logical to think, oh, the whole work is kx squared. But it's not because the force is always kx, but x isn't always 5. Right at the edge, the force being exerted is k 200 times 5 i.e., 1,000 newtons. But the force is getting weaker and weaker as the thing gets closer and closer to equilibrium, all the way to the point where at the equilibrium, the force is zero. There is no net force, right? It's at equilibrium now. X equals zero. So K times zero is zero. So all the way out here, the force is 5,000, is 1,000. All the way in here, the force is zero. So we're saying the whole work done, if you like, in a way, is not kx squared. It's not kx times x. It's the average of kx and zero. It's the average. It's kx squared plus zero divided by two. Right, like that, like I mean, we did calculus to get it. We're accounting for the fact that the force is getting weaker and weaker as it comes in. The way to do that is calculus. What calculus ends up spitting out is an answer that actually makes sense when you think about it. It's the average force times the displacement, really. Now, and then you might say, well, why didn't we just do that from the start? Why do we have to do calculus? Well, because equations are not always as easy as kx. If the equation had been any more tricky, like kx cubed, then the average wouldn't, you couldn't just like add the two and divide, like then you couldn't just guess what the average would be like that. But in this case, yes, it's like average force times displacement. That's where the 1/2 is coming from, I'm saying. All happening because the force is changing. Now, we got 3 minutes. There's 2 minutes left. A spring force is different from gravity in that it depends on X, whereas gravity does not, right? However, they have something in common. They're both known as conservative forces, unlike friction or tension or normal force. Gravity forces and spring forces are both conservative. What does that mean? Well, mathematically, it means this, and I'll pick up on this Wednesday. A If a force is conservative, we put a little subscript C, means conservative. What does it mean for a force to be conservative? It means, by definition, it means that the work that it would do around a closed path is always zero. In other words, around a round trip. What I'm saying, I'll pick up on this on Wednesday. I'm saying, well, I'm saying that if you put a circle on an integral from now on, it's still a definite integral. But instead of being from like point x1 to point x2, it's from x1 to x2 and back to x1. Whenever you put a circle on an integral, it means a round trip. It means that you end up wherever you started. It's definite, but it's round. It's a round trip. And a force is called conservative if the total amount of work it does around any closed path is always zero. In other words, if it always gives back what it took away in the first place, like gravity, but it's 12:05. So I'll continue with that on Wednesday. All right, you've been very patient. You are very patient, and you've been very participatory. All right, so thank you. I will see you Wednesday. Bye. Yes.